University of California, Berkeley, and he'll be speaking about acquiring mental models through perception, simulation, and action.
So this talk is trying to situate vision as part of embodied cognition, and I think about vision as part of this triangle: vision, motor control, as well as language, and somehow drives all of these. A key point is that all of these processes are related to each other, and it's helpful to think about. Can you hear me in the back? Okay. So a little bit of evolutionary history. So the first multicellular animals arose in the Cambrian period, around say 500 million years ago. And when they arose, they were simultaneously capable of vision and locomotion. So the two developed. Vision in this case is defined as some kind of spatial response to light, as opposed to just moving towards the light like a plant does. Phototropism is a bit simpler. Some kind of a spatial array where light is sensed. And it's kind of important because Gibson has a great line. We see in order to move, and we move in order to see. And I think that's true from the beginning of evolutionary time. If you are able to move, you get some benefit. You can find food in many different places. Of course, eventually you have predators at prey, so there's a sort of a game theoretic battle between them, which leads both to develop better vision systems, better locomotion systems, and so on. Okay. My next example was going to be about the sea squirt, but already I see that Dinesh used it, but never mind, I still have a one-side version of the story, which is that if you don't need to move, you don't need an eye or a brain. So this is an animal which at some part of its life cycle moves around, and then when it becomes stationary, it essentially digests its central nervous system. I mean, the brain in humans uses up 30% of our energy consumption. So if it's not very good to you, then why bother to take them this way? I mean, the way to think about it an example, trees, right? So trees, if they evolved vision, how would it help them? I mean, they might know that yes, there's an animal coming to eat up the leaves, but it would not provide them any evolutionary benefit. This example is usually quoted to show why tenured professors do not need brains. Okay. Moving on to not the last 500 million years, but the last 5 million years, you have the development of manipulation. So, in the private line, there is this bifurcation when bipedalism developed. So we had our hands free because we could move around on our two legs. And once you have that, the fossil record shows that there is a development of the hand and the development of the size of the brain, which go sort of together. And roughly speaking, it's really the hand that drives the development of the brain, rather than the other way around. There is this Greek philosopher more than 2,000 years ago who had this great line, which is, it is because of his being armed with hands that man is the most intelligent of animals. It's not that we are intelligent, therefore we have sophisticated hands. We have sophisticated hands, which led us to sophisticated brains. Okay, so that's 5 million years ago. After that, say 100,000 years ago, we have the development of language and symbolic reasoning and semantic reasoning, and there are many theories of this, all captured in this one slide, but I won't go more in that. Okay, big picture. So these are the main components of intelligence: vision and locomotion, manipulation, and language. And so 500 million years, 5 million years, 100,000 years. And interestingly, I think successes in AI follow more or less the same order. So of these areas, what has shown the most success? I mean, right now, I think vision is greatly successful in tasks such as object recognition and so forth. We have kind of cracked the essence of the problem. I mean, of course, we'll keep improving things, but the basic problem has been cracked. If you put locomotion, in this case, means mobile robots. You put vision and locomotion together, you get self-driving cars. So it was inevitable that self-driving cars come at this time in the history of AI, because it essentially corresponds to vision and motion working together. Manipulation, we are quite a way short. And I think a big part is that this hand and the parallel jaw gripper are quite different in capabilities. So we do the best we can, but still there's a long way to go. And certainly language, I think when we talk about language at the level of symbolic understanding and so forth, I think things are a long way off. Our success in being able to translate from English to French as sequences of strings is, to me, feels more like sort of a Chinese root kind of an argument rather than real, genuine understanding. Okay, so now back to sort of vision. We are so if we look at a scene like this, what do we see? So first, I want you to try to appreciate what you infer in this scene. Okay, so you probably see these people. You sort of notice that this woman is a musician. She's got this bag, and there appear to be dollars there. Maybe this guy is looking at her. Somehow you have this rich structure of social interactions. Okay, what can computer vision do today? We can convert it to some kinds of objects and attributes. We can say a person A walking away carrying the bag. Maybe we can't do this perfectly, but you can imagine an extrapolation of current techniques which would do this perfectly. So you recognize all the objects, maybe you even map 3D models in a certain pose and so forth. Okay, but what is it that you can't do? Okay, what we can't do is something like, okay, is this man going to put some money in her tip bag? So this prediction of what's going to happen in the future, we can't do this. Okay, then I'll mention some, again, general remarks. What has been responsible for recent AI successes? So everybody would recognize that big computing and big data is a big part of it, right? Without this, I mean, the neural networks techniques, a lot of them, practically all of them, sort of date back to the 80s. Okay, we have some twists like using reduce and dropout and so forth. But more or less, the ideas that go back to the 80s. But they are much more successful now. Well, we have GPUs, we have the internet in between, we have huge amounts of label data. I would like to argue that we should give appropriate acknowledgement to that. So our successes are not due just to big computing and big data. They're also due to big annotation and big simulation. So big annotation is essentially the availability of Amazon Mechanical Turk. The image data set, which has 1 million images that took a long time to label, and of course many others such as like that. And big simulation. So here are some of the successes. So these are the successes for DeepMind, so the success at Go and Atari games. And but if you think about it, these are a rather narrow slice of what AI is capable of. Because in these scenarios, okay, first of all, games. Games are games of complete information, so there is no uncertainty there. Okay. The Atari games, these are ones where simulations work very well. So therefore, these techniques which require you to use reinforcement learning with zillions of trials become effective in this setting. Now, in the real world, when you have a physical robot, nobody is going to let you do 1 million trials with your physical robot. Okay, or probably in the course of it, the motors will wear out, and some chaos which will happen. Anyway, nobody will let you do this. So it's not clear that the success of this immediately scales into settings, the ones that we really care about in intelligence, in robotics, and so forth. So contrast this with how children learn. So what did we have? We had big computing, big annotation, big simulation, big data, all of these. Okay, now let's contrast this with how children learn. So we know quite a bit about how children learn. Here are some pictures, and it's clear that there are various stages of development which have been very well mapped out. starting from the work of Piaget nearly a century ago to the more refined techniques which people have used in the last 30 years, such as preferential looking. The stages of child development, their capabilities of influence are much better understood. And the key thing to realize is that the child is not just a passive sensory motor reflex device. There are quite a few capabilities built in. The child is an active learner. So my colleague Alison Gopnik has a book whose title is The Scientist in the Crib, because the babies are actually conducting experiments and they have hypotheses, from there they are building better theories, and that's how intelligence develops through these various stages of construction. It's not just parameter tuning of something. So let's contrast this. So at the top you have supervised learning. Okay, the mother says zebra. Okay. Now, if we want to consider how image-led training works, this mother would have to point to 10,000 zebras, and then to 10,000 okapis, and then to 10,000 horses, and 10,000, maybe 1 million dogs, and so forth. But is this the way it works? No. I mean, I've actually done a little bit of this, very informal version of this experimentation with my son when he was growing up. And essentially, you need one example, right? I tested him specifically for elephants, and he seen elephants in a flat setting. We went to a zoo, he knew that it was an elephant. We went on a trip to India, and there is this elephant god who's half an elephant, and he knew that was an elephant. So that level of abstraction is amazing. Okay, so clearly this mode is not sustainable. It's great for engineering today. Okay. If you want to have a company in Silicon Valley and you want to succeed next year, the best would be that if you find a setting where there is some data which you can somehow get labeled, and I think that's the secret to success right now. But long term, we kind of have to look at ideas such as this, where the child is conducting his or her own experiments and using that to supervise its own behavior. So I can't get into the whole literature on child learning, but there is one paper that I will advertise because the literature is formidable. Just like for somebody in child development to come into computer vision or machine learning and try to master the literature, it won't be easy. But this one paper I think is a good review, and it's by Linda Smith and Michael Gasser. And the next slide, I'll just show you what the 6 lessons, they've tried to boil it down to 6 lessons. One is being multimodal. So when the child interacts with the world, so the child takes a toy, so it's reaching out. So at that point, the motor system is involved. So the proprioceptive sense is being exploited. There's touch, there is vision. So somehow all of these there might be sounds produced. So all of these are playing together. Incremental, there are stages. So you can, in machine learning, we might use the term curriculum learning, but it's very sophisticated. In fact, some of the limitations of the visual system at early stages, such as the fact that infants' visual system is very blurred, has been argued to be a positive thing, because essentially it enables force to find reasoning. So you're not getting distracted with the details. Be physical, you're interacting in the physical world. And note that I am a vision chauvinist, but vision is not fundamental to this. A blind child also develops a model of the world that perfectly well uses language with all its spatial metaphors. They would use terms like look there, and this person could see far, and so forth. And the reason is that they develop their spatial sense through that tactile sense plus locomotion. So vision is not critical, perception is critical. Something to develop a spatial reasoning is critical. Be social. A lot of what we learn is through interactions with caregivers and in modern industrial societies through schooling and so forth. I mean, currently the leading paradigm for learning of action is reinforcement learning. Now, this would be as if you were this primitive caveman who had to explore and figure out everything by himself or herself. This is not how it is, right? We go to schools, we are taught by professors. I think that we add some value, but maybe I'm wrong. If you are a blacksmith, you are an apprentice with a senior blacksmith, and so forth. So really a lot of learning is in fact imitation learning. And then, so reinforcement learning does play a role, but I think currently in our community we are overplaying it. It is very nice and elegant. So no wonder people are excited about it because it has this flavor of you're not building in too much. But if we think about human learning, I think it's a small component. It's very hard to make it work, and it's a small. Fortunately, it's only a small component of what we do. Okay, finally there is language, and we have thought often about language as coming on top of perception, but there are experiments which indicate that in fact language guides perception. So the fact that there are multiple words may give you the signal that these are two different perceptual categories, and there's evidence of that. Okay, so this was general stuff, and now what I'm going to do is take you through a few case studies. So I think there's a research agenda here, which is to develop AI on the basis of child development. Now, obviously, all these psychological findings are a bit fuzzy and so forth. So we have to develop a very clear mathematical or computational formalism to do this. And there's not going to be a grand theory which will emerge immediately. What's going to happen is we're going to have successful cases, and then we'll see the pattern, and then more people will get into the field, and soon this will become the dominant paradigm in the field. So I truly appreciate this workshop because it's an attempt to pull together this emerging area. Okay. How much time do I have now?
About 15 minutes.
Okay. So now I'll get into some concrete results. So, okay, so what kind of information can, this internal teaching, so think of it as some kind of self-supervision. So, okay, let me go into another one of my rants. So it's very popular to say, okay, we've been doing supervised learning and what's important is unsupervised learning. I find unsupervised learning is a very, it's too generic. It's not really a category. Unsupervised learning by itself, if you think about it as a statistician, it evokes finding patterns in data such as clustering or PCA or some version thereof. I think that if we think about human learning or child development, there are many flavors of learning and a lot of, the examples that I listed earlier of the nature of child development suggest that. A lot of them involve self-supervision or of some sort. And I think we will need to use specific terms corresponding to those rather than try to throw everything under the generic umbrella of unsupervised learning. Supervised learning makes sense, reinforcement learning makes sense. Those two terms are quite meaningful and they give us a strategy. I think that unsupervised learning is got to be broken up into many different subcategories. Okay, back to this issue of how does a child like this learn? What kind of information can such an internal signal provide? Okay, so let's take an example. So this is an experiment, right? So I said the book by Alison Gopnik, the scientist in the kid. So a child does an experiment. You poke a Coke bottle, you poke this ball. Okay, the Coke bottle falls down, the ball rolls. But in this little experiment, you are a physicist, right? You are an Aristotelian physicist, not a Newtonian physicist. But I would argue that Aristotelian physics is what's more important for us. So in the physics that I care about, if you drop a marble and a feather, they should have different behavior. And that's perfectly okay. Your perception leads you to record these as different kinds of behavior, and that's perfectly okay. I think that's the behavior we need. That kind of naive physics is what we need for much of acting in the world. So this is one interaction. Now, what's important is that you applied that force. So therefore, you know what you commanded. And this idea has been around in neuroscience since the 19th century from people like Helmholtz. They use the term efference copy. So efference copy, which is say specifically talked about for eye movements, the brain commands the eye to move, right? So So therefore it knows what's the amount of rotation that it commanded of the eye. So in tasks like if I'm moving, so typically when I'm moving, there's a translation and then there's a rotation because the eye might be fixated at that object, for example, the speaker. So now you have a rotation and translation and you're trying to do structure from motion where rotation and translation are together. Well, experiments have shown that essentially the rotation part, the visual system just knows, quote knows, because the rotation part was the rotation of the eye which was commanded by the brain. So we have very good evidence of this, and there are examples of this from the motor control. So just assume that we know what we did. So here's another example. So this is a purely visual interaction. You look at this object and this chair, and then you turn around and you look at it, you move, and then you see it from a different angle. So the object appearance changes, and but the visual rotation is known to you because you commanded it. So how do we exploit this? So one canonical way to think about it is there is an input image, there is an output image, there is an action, and you know the action. Okay. So what you can try to do is you can try to predict, given this image, what will be the output image. Now trying to predict an output image is hard, right? So there is all this action in adversarial links and so forth. But let's see if we can get out to this. Basically, you have a relationship between an input image, an action, and an output image. So that's a triple. And you can worry about, given two of them, predicting the third. And life might be easier if you say, I care about the input. Given the input and the output, I predict the action. But of course, you will know the action. So it gives you a sort of a training routine which goes like this. So you have an initial state, a final state. Both of those are available visually. You did the experiment. So this is experimental learning. You do experiments and you collect measurements as you're going along. So there's the initial state, the final state. You did a poke, so you know it in advance, and you try to predict the poke, and that gives you a loss function with which you can try to train the network. Similarly, for a visual interaction, you have an initial image, a final image after the observer has moved, and so you know that. You run both of them through a Siamese network and you try to predict the ego motion, which you actually know. Yeah. So that's the idea. We had the paper of this at ECCV 2015. And there what we did was there's this data set Kitty, where you have a car driving through a street and you have multiple views of images, so the ego motion is known. And this becomes a device for feature learning. Okay, and I think I already listed the idea. Then one can then use this on, so there's no supervision needed, or rather I would call it some kind of self-supervision. And then we can test it on how the resulting representation helps you on standard tasks like recognition. And it gives you something. It's not as good as pre-training with ImageNet, but it's reasonable. Although in my mind, this is what everybody in this business does. We all try to prove that our representations, which have been trained on these auxiliary tasks or pretext tasks, are actually good for something. And then you go back and try on Pascal or this. But in a way, this is silly. You spend a lot of time building scissors, and then you evaluate on whether it's a good hammer. Okay, because that's how the way you get your paper in. But anyway, I hope we'll get out of that at some point. So I'm going to cut these other examples out of this. And okay. And here are some other papers which all came out sort of around ECCV 2015, which has this sort of idea. Okay, now let's see. Let me move along. I always like bringing history into it, and this is one of my favorite quotes. I mean, Drake was an outstanding scientist. Look up in Wikipedia. He died in a bicycle accident in 1943. But in a certain way, his thinking is the precursor to cognitive science as well as modern control theory. So this idea that you have a mental model in which you can simulate, so that's the simulation of our is very important. So control theory, you sort of make it more restricted. X dot equals ax plus bu, y equals cx plus bu, and so forth. So that state space formalism is version of this. Cognitive science you get out of behaviorism and to mental models. Okay. Now, how do we take? So I think that now with the kinds of tools we have of learning, deep learning, I think we can take this idea and operationalize it in various different ways. So here's some work. So we need to have a model of an agent and environment. So the kinds of things we've done in our group include, for example, understanding, building a model of billiards. Okay, so we want to understand, we want to develop an agent which plays billiards. So you want to know what force to apply, and so you have a model of agent and an environment. So the paper right now. Note that if this was the only task, I mean, that classical physics-based simulation would do the job. However, we use this as a test bed for the learning-based approach to acquire dynamical models. So you want to generalize over these kinds of variations. And what do you do? The training setup is you have some initial state of the board, you apply some force, you predict what will happen, you know what actually happens because you can do a physical simulation. And you do the usual CNN, LSTM, mumbo jumbo. Okay. And then as a result, you can build a model of how the physics operates. Okay. And including collisions with the wall and other balls, etc., etc., and then you can use it for planning. So the important part is a model of a dynamical model. I mean, control theorists have always known this, right? They think in terms of this x dot equals ax plus bu, y equals cx plus du. That if you have a dynamical model, then you know what control input to apply. And it's just that their tools are classical, and now we can use these nonlinear tools. Okay, so blah blah blah. Okay, but let me give you an example of where the physics-based approach won't work. So I'm interested in all kinds of prediction problems. So here I'm interested in predicting, here is a player who has the ball, the yellow ball. Who will she pass the ball to? Once the ball is in the air, it's a problem of Newtonian physics. But before the ball is in the air, it's a problem of sort of human thinking and cognition and so forth. She is planning who are the players or my team, who's the one closest to the goal, who's good, you know, all of that stuff. Okay, so now I'll run through one more experiment, which is learning to cope by coping. So this is coming out at NIPS. Let me give you an example of this. Okay, so here again, I think it's experimental learning. So the terminology I want to use is there's reinforcement learning, there's imitation learning, and then there's experimental learning. There is not a long sequence, but you do lots of experiments. Okay. So basically what you do is you poke in various directions, and you have an image before and after. Okay, so the network, so same trick. Trying to predict images is painful. Try to predict, but you have this triplet, initial image, final image, and then action you perform. And you try to, given any two, you try to predict the third. And so there is a forward model and an inverse model, and both of them have value. The inverse model is what you use for planning. The forward model is what is capturing your physical understanding. And it turns out that you can, it's a useful thing, and I'm skipping details, the paper is on archive. You basically you train a forward and a backward model at the same time. So that the training data which you have are these triples, and you try to train a forward model and a backward model at the same time. And that's shown here. So there are two images. So there's a forward path which is given these two images, it's trying to predict the action. And there is there you go. And then it does interesting things. You can do these experiments, and it sort of acquires these forward and backward models, and then you can guess the new situation. And okay, some numbers. And I want to, of course, mention that this is our group has been doing this in parallel. Certainly, Abhinav Gupta's work gets group as CFU, and we are going to hear from him in the afternoon.
Yes.
And also, he's been trying to experiment with grasping tasks and so forth. So again, I think this is an interesting field where the state compared to what happens in reinforcement learning, this is relatively shallow learning, right? You don't have a long sequence of actions at the end of which you get a reward. You perform immediate actions and you directly have a measurement of whether you succeeded, what happened. I mean, the output may be richer than just what happened. Whether success or failure, the output is a new state. But I think it's a good paradigm. And I'll conclude with my opening slide. I think we Vision people have been very successful in the last few years. And deep learning has really made a big difference in our ability to do recognition. But we now need to move beyond that. In fact, vision, control, and language are all coupled together, and I hope we see lots of research in this triangle. Thanks.
Thanks, Professor Malik. I guess we have time for a couple of audience questions. We also have a panel discussion at the end. So.
Very, very nice talk. I have a question. If we have solved basic perception tasks like pose, or if we're on the verge of like pose, object recognition, etc., why do we need intuitive physics when we have mathematical physics? Meaning, why do we need to embed in the weights of our networks physics by providing examples generated using physics simulation or real physics, versus trying to incorporate the laws of physics in the architecture of the models? So weights versus architecture.
Okay, good question. So we know the laws of physics, but we do not know the parameters of the real world. So I'll take an example which is about physics, but the physics of light. So optics, right? It's been known for the 19th century. You have the basic models of Lambert and BRDFs and scattering, and I mean very sophisticated stuff. Okay. However, then what you have is this question of what would a piece of wood look like, or how do we render hair? And these are very hard problems. These are not hard problems because the laws of physics are not known. The laws of physics for optics are known a century ago, yet the graphics people took like 30, 40 years to work it out. And the reason is because how to model it efficiently, computationally, plus all the parameters. The parameters change. So the physicists are not interested in that, right? They've written out the laws and now they don't care about the parameters. Now what we care about is, in fact, to acquire those parameters through learning. So in graphics, which has a long history of tackling this, we can imagine trying to estimate the parameters through physics type techniques and then putting them into our simulation. And that's one approach. Another approach is to directly work from image data and not get into, quote, the underlying true physical state. And yet, from that, you have enough information to predict new images. That's what's called image-based modeling and rendering. Okay, now the same is true in the physical world. Physical world, again, I would distinguish between movement in contact and movement in free space versus movement in contact. So in free space, Newtonian physics is kind of easy, except for like wind resistance, etc. Okay, but movement in contact, so you're touching objects, grasping. And the grasping has been around for 30 years, and there are these models of grasping. But these models are very idealized models because they're really models of the geometry, and the physics doesn't take into account certain things. So when these experiments were being done by people like Abhinav and versions of those experiments at Google, if you're trying to pick up a bag of potato chips, there's different behavior because the thing yields. Now this is not captured. You know it because you do experiments. You're always picking up potato chips, and now you know that potato chips and rubber balls and iron hammers have to be treated differently. So it's sorry a long-winded answer, but it's a very interesting question because I come from a background where I would have rather modeled the whole thing, and I hated this learning mumbo jumbo once upon a time because I felt that if we could understand that is better. But we do want that deep understanding, but the fact that there are so many unknown parameters actually leads us down this learning approach.
Thanks, Professor Malik. Okay. We'll have Professor De Freitas set up. Professor De Freitas will be speaking about learning of policy again.
Thank you for the invitation. How's my voice at the back? Here of you aren't going to wear a microphone. Microphone? Let's see. Now? Yeah. First of all, thank you, Dan, for inviting me here. It's a great pleasure to be back at ECCV after about 12 years since I last was here. 14, something like that, long time ago. And one of the reasons why I left is a video that I will show soon that has to do with agents being embedded in the world with action. And at the time when we were just doing histograms of features, I felt that that was not the way to do computer vision. And so I went the RL route. And I think now we're finally coming together again. We're starting to look at interesting problems. It's going to be really hard to follow the previous talk, but it's really inspirational and it's spot on. It's about like what the kind of research that we need to be doing, I think, if we want to make progress with understanding intelligence. So I'm going to, like this title sort of alludes to, this is going to be sort of Trumpian agents. So this is going to be RL brute force agents that I'm going to be talking about. But even though this is a very small part of the puzzle, for that baby interacting with the environment, poking something, the sort of very basic type of RL turns out to be very important. It's essential, and we need to know how to do it well. Just like we needed to know how to learn features properly. There are some of these very basic parts of cognition that we need to get right. This is work with several of my collaborators at DeepMind, and in particular with Ziyu Wang, who's responsible for many of the ideas I will present here today. So we're working under the standard RL framework. My talk will be a bit more dry instead of going for the general view. I'm going to just be talking about a simple setup, not even model-based, but model-free, in which we have an agent that makes observations from the environment and then acts upon the environment, and it's in closed loop with the environment. The agent and the environment are essentially one. I think the view of embodiment that was espoused before with this sort of agents, part of the agent itself is the environment. Because in a sense, the moment I grab this and I start looking at this is sort of me. There's very little distinction between you and the environment and you and another agent. I think it's just for understanding that we make those divisions. What I'm showing you here is a very old video. It's called the peanut butter jelly sandwich video. That dot there is your fixations of a subject. And I got this thanks to Dana Ballard many years ago, I think around 2002. And what it's showing here is that your perceptual system is not focusing much on trying to label the things that are there in the scene, but it's just basically being used to do, the vision system has been commanded by what sort of things you're doing. And in particular, look at what's going to happen as you pour this drink. So vision here is focusing on the edge of the glass. And that makes sense. If I'm pouring liquid, what I care about is not overflowing, as opposed to trying to label things. Okay, so I think this is something that we all know, or at least this room knows, because I think this is going to be, in about 5 years, most of computer vision will be solving these type of problems that Jitendra posed before. So you have a good start, especially students. Now back to RL. Actually, one more, I'm going to do like Jitendra, give pieces of wisdom. I recommend you look as well. So I've come to understand a lot of the things Jitendra was presenting, partly because we've had the benefit of having some of his students visiting DeepMind who I've been working with, Wilkit and so on. But also because one of my good friends, George Tenenbaum, he and I talk a lot about like what's needed for coordination in AI. And he invited me to look at Elizabeth Spelke's work at Harvard. I strongly recommend you look at that. I might not agree with the conclusions in the end, but her work on core knowledge is really outstanding, and I highly recommend it. So I think we had Alison Gopnik, Elizabeth Spelke. They talk about things that are very important, about how we come to understand what is an object. And I'm going to leave you with that question to think about for the panel. What is an object? I don't know the answer to that question, but these very sort of obvious things turn out to be, I think, very hard. Okay, so in the RL setup, the quantities of interest are states or observations of the world, actions that the agent takes, and then I'm going to assume that the agent has a policy, and the policy will be, as Jitendra said, the usual mumbo jumbo. So in this case, a COVNET that predicts the probability of the actions given that observation dx. And then the goal will be a very sort of, in the narrow sense of RL, will be to maximize future returns or future rewards. And this, the sum often uses this hack called discounting, which is basically we multiply the rewards by this gamma, so that future rewards are sort of less relevance than more immediate rewards. If we look at the expectation of these returns of all the future states of the world and the future actions that you might take, you essentially get the expected returns. So if your returns are that green bar, and you imagine traveling from this side to the right, as you're getting close to the reward, you should expect to get some reward. That blue curve is this function here. It's your expectation as you're approaching. And when we do these value function RL methods, this is what we do. Actually, before I sort of bore you with details of RL, how many people here are familiar with RL? Okay, half of you, so I'll go half speed. The expectation of that state action value function is known as just the value function. Sometimes we use deterministic cues, so we look for the argmax of array. So it's the probability then the policy is just one spike. So the expectation in this case is just at the max of the Q function. And we also define a quantity called the advantage function. It turns out to be actually very useful. And the advantage is just the difference between the Q function and the V function. If you take expectations on both sides with respect to the policy, then because V is the expectation of Q, it must be that the expectation of A is 0. So the expectation advantage basically is something that tells you, regardless of state, or it basically ranks actions. Which action is better to do in a particular situation? Now, one way, the effective way of doing reinforcement learning problems for the type of things when you're sort of poking in an image and so on, is to do policy gradients. And this probably, if you have to learn algorithms, for computer vision, this is the one I recommend. This is the one RL algorithm I think people have to know. I'm not going to give you the derivation. I have a course in YouTube that I recommend that has a derivation of this equation. I also strongly recommend a paper by John Schulman from Berkeley, who's now at OpenAI, on advantage learning that derives this equation. This is the equation of the gradient of the return. So if you want to maximize the returns, you do a little bit of math and you end up with this expression, which is again the expectation over all the future trajectories of the sum of these advantage functions times the derivative of the policy. So all you need to know is how to compute the derivative of the policy, that network, in order to be able to maximize this. Of course, to take that expectation, we're going to have to, that's what the trick is going to be. And there's many variants in which you could do this, and these are all correct versions of doing this. So you could take the advantage function, you could replace it by a Q function. If you're, I guess, from Alberta, you're in Sutton's group, you would do that. So this is the usual thing that most people use, because the Q function is an estimate of the reward function, so it's the return, so some people use this. And you may even use this, what people call the lambda returns here, which is essentially, this is basically the Q function, this guy plus this guy, and so this just looks at the difference of two steps. In the paper of John Schulman, you'll find a proof showing that you can plug any of these into that expression and it will give you the same unbiased gradient estimates. Now, what is important is some of them will introduce different errors. If you try to model the advantage function or the Q function, or value functions, by using neural networks, then we're introducing bias, we're introducing approximation errors as well. If you just do Monte Carlo returns, there's no neural network except for the policy, but then this is going to be very high variance. And essentially what the whole game in our realm of policy gradients is how you trade off bias and variance and how you try to get rid of both. One solution for this, and this is one of the most effective methods out there right now, is something called A3C for a synchronous advantage actor critic of lab need. And the network that they use is again a standard comp net that predicts both the policy and the value function. So it's like a network that it splits into two heads. We can use recurrent connections and sort of at the output some of the layers. And that's the way of dealing with partial observability. I think one important thing is over the last bit of work with neural networks is we no longer bother with things called POM VPs that we used to bother in AI. Thank God that they're gone because they were incredibly hard. Typical neural stack programs. Now, what Vlad's done here is he's sort of trading off bias and variance. The way he's approximating that advantage function now is by saying, let's do the returns for case steps. So we're going to sum the rewards up to 4 case steps. And then after case steps, we're going to use the value function to estimate the rest. So he has that term B theta at xt plus k. And then the next term is just a variance reduction technique called bias reduction. And the algorithms for this, I'm not going to go over it in detail, but they're very simple. Typically what you do, follow a trajectory of case steps. And that trajectory is essentially what you sample it by behaving in the environment according to your neural network. So basically, given the axis, you predict which actions you're going to take. And then you need to run it on the environment for case steps. And after running it in the environment for case steps, so in other words, you're sort of approximating your expectation, that big expectation we had before by a Monte Carlo rollout of case steps. So we do that, perform those actions, and then we just go backward and use the, essentially here, we start by initializing the value function, and as we go back, we sum all these returns. So we compute this reward function, and then we take the gradient step, which is just basically the thing that we have upstairs. And then in order to estimate the Q head, the value function head, you minimize the quadratic difference between the value function, which is an estimator of the return. So the algorithm actually, is sort of scary math, but the algorithms end up being quite simple. It's getting the details right that is challenging here. Now, these methods are called on-policy methods because you're acting on the world using the policy that is the policy that you've with which you model the MDP. However, they turn out to have an important disadvantage, and the disadvantage is tied with the type of applications that we saw in the previous talk, and we've seen by many of the other folks that will be presenting their work here today. Is that whether it's environments or the real world, they're becoming very expensive. You know, these environments are reasonably cheap. These Atari environments, as we're moving more toward the sort of very rich environments that everyone is using, here I think that's Alan Institute, we're starting to pay a lot for rendering those images. So all of a sudden, experiments that we used to run in 2 weeks with 100 GPUs or so many thousand CPUs, all of a sudden now will take several months. And we are doing a lot of work to improve rendering, speed of rendering and so on, but still querying the environment is expensive. Now, for those of you doing ImageNet, you know that there's a trick around this, which is don't just do one pass over the data. Don't just collect the 1,000 zebras and then gain another 1,000 zebras, but rather just do several passes over the data. And that's essentially the notion of replay or off-policy learning. So we're going to continue learning, even though we're embedded in the world, by using whatever policy we use to collect the data, by using a different policy. So we're calibrating. And this is related to causality to use of counterfactuals as well. So there is a traditional way of doing this sort of policy learning. So basically the idea here is you want an agent to act upon the environment, and then the agent should be able to store the information that it has been gathering, and it needs to sort of replay those past experiences in order to sort of improve what it does in the new situation. In a very simple way of doing this, like imagine that the agent has a trajectory of states, actions, and rewards, and some behavior policy, which I will use, called mu. And what the agent now needs to do is needs to maximize the expected reward, but this time, the policy of the MDP is pi, so because it's behaving under this other policy, it needs to correct. And the simple way to do this correction is by importance sampling. So you still have the same estimator for doing a trajectory of case steps, but now for each time step, you need to correct with these ratios. So you take in an expectation, essentially, we take an expectation with respect to pi, we convert it to an expectation of a mu, but then we need to multiply it by this ratio so that you have the right expectation. The problem with this is that you're multiplying k terms of this nature, k products of probabilities. And so all it takes is for your behavior policy to assign very low probability to where your true policy of the MDP has high probability for this thing to bomb out. And in fact, most of the times, this estimator will bomb out. It's too high variance, even though it's one of the most popular ones used out there. An alternative was by De Klee and Rich Sutton called the off-policy actor critic. And what the off-policy actor critic does is it considers this thing here, which is the invariant distribution of the Markov chain, or basically if you're acting, how many times ad infinitum would you visit a particular state. So basically the probability that the Markov chain has converged to. And that allows them to rewrite this expression in a much succinct way, where now the importance weight only depends on time t, as opposed to depending on a whole trajectory. And that can be exploited to get an estimator that has much lower variance. So in particular, what one can do is one can approximate that expectation by, we're going to do Monte Carlo returns as well. But when we do Monte Carlo returns, because of the way it's constructed, the importance weights will only happen at each marginal time step. So we don't need to take a product of them, but we're going to be taking a sum of them. So we're going to be in better shape. Now, a single importance weight can still bomb out. And so we're going to do another trick, which is we're going to truncate. Every time the importance weight is above a certain level, C, we're going to cap it at C. Okay. And this truncation can be done in a way that doesn't introduce any bias or variance. In fact, the expression up there, which is for this of policy actor-critic, is the same as the expression below. I don't have time to prove that, but it's possible to decouple it to a term that's essentially like the top one, where the importance weight is now controlled, is truncated, and another expression that corrects for the bias. And you can just check both cases by looking at when greater than C1 less than C. And this term is less than 1, so this will be well behaved. So that's one trick you can do. And then that Q function there still depends on the optimal policy, but we can approximate it with the neural network. And we're not yet done because we still have another Q that depends on pi, but we can use another trick that is very useful. Training into RL, these other tricks you need to know. Retrace. It's a recent paper, 2016, one of the best RL papers of the year, I think. It's a very simple variance reduction technique. The usual estimator of Q is just R plus gamma V. And what Remy Muniz does is he adds this extra correction. And he proves that this update to the Q function is a contraction. So in other words, it will always reduce the variance of Q. It's a fixed point and it will reduce your variance, just like when you do the power method or when you do the Google PageRank algorithm. You keep multiplying by a matrix whose entries sum to 1. So you're basically doing successive conditional expectation, and that is a contraction because conditioning reduces variance. So you're much quicker converge to the invariant vector. And here by using this, we're going to reduce variance substantially. And you can plug that into our estimator, and we get an algorithm that's now of policy. It's very similar to the other algorithm that we had before, but now the importance weights are truncated. You were adding them successively, so we're not taking products of them. That's very important. We're using these low variance estimators for the Q function. And we're using all these corrections to ensure we don't add bias in the process. And then we also estimating the Q functions. And if you do this and you run this in Atari with discrete action, and one of the reasons for doing all this work is that this type of algorithm that I've described so far, I haven't told you whether the actions are discrete or continuous. Most reinforcement algorithms make that choice. This technique will work for both. When the actions are discrete, say in Atari, these are the sort of experiments in terms of comparison with respect to human performance, and a random agent would have performance at 0, and a human would have performance at 1. And by human, I mean a game player, professional gameplay. And this is what DeepMind had in their Nature publication. So we've kind of come a long way from that. Actually, I'm following
6 more minutes.
6.
Yeah.
Thank you. So we've come a long way since this publication in terms of the type of algorithms that we're improving, which gives me indication to think we still need work to do in this very simple type of RL. But again, the warning is this simple type of RL that I'm talking about today, even though necessary, keep in mind this is just Piaget conditioning. This is the most trivial form of RL, which we still have to get right, but we will have to bring in models and imagination, especially the sort of models that are going to imagine the future that are essential for thinking. And in fact, planning and imagination are very intertwined. We need to think about the future because acting in the world can be very expensive. Like, again, you're going to like this example. Like if you're going to do something that's irreversible, for example, if you're going to have come up with derogatory comments about women, you should think about the possibility that in the future, 4 years down the line, you might be running for president of some nation. There's other reasons why you shouldn't come up with derogatory comments about anyone, but we in the world encounter these irreversible situations. And if you have an irreversible situation, you need to think about it. Acting is just too expensive. You could die by acting. So you really need to think about it before what you do. So this sort of planning by simulating the future is essential. These models have a very limited capacity of doing this. I think we need to keep improving. But even with these models, this was what won, or what had that nature paper. This was the A3CA framework on policy, and by doing something called replay, prioritized replay, by deciding which experiences in your memory are more important. This is a paper we, using some network architectures I'll show soon. This is a paper we had at ICML recently, and this is one version of the algorithm here in red, where we do several steps of replay that I sort of be discussing, the one that was in the previous slide. This is in terms of environmental steps, sample complexity. In terms of computational complexity, they're all about the same, except for the thing we published in Nature. But again, the argument here is that in Atari, this doesn't matter, because Atari, the amount of rendering you have to do is minimal. But if you deploy these agents in the real world, then you do need to worry a lot about the plot on the left. That becomes your relevant one, because actions in the world is what counts, what's expensive. There's also been some development in terms of network architectures. In order to get the state of the art for Atari, we had to actually go from the standard couplet to add an extra module at the output. And what that module tries to do is this network basically outputs Q functions that's model used in Atari. This other one will also output Q functions, but will first output a V function and then an advantage function. And the V function gives you the value of a state. The advantage function gives you a ranking of the actions for a particular state. Importantly, in some states of the world, you don't need to consider all possible actions, because only some actions are relevant in some states of the world. And so we're going to exploit this to do faster learning. And here's an example of this at play. By computing the gradients of that architecture, starting at the value function and then starting at the advantage function, I can compute this sort of with respect to the input. I can sort of overlay those gradients on the image, and that's what you're seeing here. So in terms of value, this is what the network pays attention to. It cares about where to go in the road. It cares about the score. The advantage function is there's no attention unless there's a car immediately in front. Because you only need to take action when you confront, when there's a car in front. Otherwise, your actions are not one prefect to the other. And then we've extended this to continuous state spaces more recently, and the paper is still not on archive, should be in archive. Actually, this talk should be in archive in a couple of weeks. Using these dueling architectures, we've been able to extend this algorithm that I discussed before to continuous state space. And we do one more trick that turns out to be an extremely important trick for anyone doing ARA or GANs or any of these estimators. Actor critics, by the way, is just it's a generalization of GANs, generative adversarial networks. The critic, that Q function is a way of measuring the performance of the actor, which is the policy, which is, say, the generator of GANs. One of the things with these methods to estimate them is extremely hard. They're very unstable. So anyone working with generative adversarial models will tell you that it's very hard to stabilize these methods. And it's the same for policy actor critics. In fact, this work is the first to have stabilized them and run them at this scale. One of the things that is key to get this to work is first we model the policy as a neural network that outputs, in this case, some features of a distribution F. So think of the mean of a Gaussian. So you're predicting the mean of a Gaussian distribution. So pi is the mean. And then we're gonna also have a slope average estimator of the policy, beta A. And then this is what we do. There is a related paper by John Schulman and Sergey Levinets on how to do this. Their method is quadratic, it's very expensive. This is a cheap way of doing it that actually works extremely well as a season. So we try to match the gradient. We try to estimate this alternative slope gradient Z. And all we need to ensure is that the updates between the slope and the fast are not too far from each other. So we're going to do something like what's known as the natural gradient. Importantly, we'll measure the distance in terms of the outputs of the neural network. We're only going to take derivatives with respect to the derivatives with respect to the output. Another way to think about it is we're changing backpropagation. That first message that goes into the top layer, we're modifying it. We're not doing exact backpropagation, we use a modified form of backpropagation. And then after that, with respect to the parameters, we just backpropagate the messages now. Since it's my last slide, I'm just going to show you what happens when you do this for controlled tasks. So this, I guess, is the second step in evolution, which is we're trying to go from just perceiving to actually get the locomotion right. And I'm showing you here several estimators. And for each of those estimators, just to, you'll see that doing this, stabilizing the policy by doing this trust region optimization can have a huge impact. So first of all, let's look at the dashed line. So those are the techniques that I've introduced. So they tend to, the dashed line is the important sampling estimator, the old estimator that existed. So this is in red. So this is the naive estimator. This is just the important sampling. And in red, you see it without doing the stabilization of the policy, without press region. Just by changing that optimizer, gives you this huge performance boost in all these methods. In red, of course, is our technique, the one that I've introduced. It does better. But what's really important here is not just to see how the improvement that you can get by going off policy and doing replay, but also the improvement that you get by thinking about how you stabilize those policy updates. And I think I'm out of time. Thank you.
Thanks, Professor De Freitas. We can take a question or two from the audience. Okay, so let me ask the question. You showed us a trick for using off-policy learning to make, to use replay and use the trials that we have more efficiently. So what else can we do to kind of make RL more feasible for actual visual setting, robots and so on? What are the technical challenges out there before we get to that?
I think for robotics, everything I've talked about today is essential. In fact, I think this trust region policy optimization, replay, and all this sort of variance tricks. That this is what will make it work. But this is sort of for very basic robotics. So we're having something going from immediate vision to action. But if your robot starts doing more interesting things in the world, then that robot is going to have to imagine. It's going to have to start building models and being able to do this imagination-based planning. That we're still very far from that. We haven't attacked that problem yet. And of course, there is also this problem of that I think is extremely important, which is we're using simulators for a lot of these things, and we're transferring, even though I didn't talk about today, we're transferring what these robot-type simulators are doing to the real world. So there is this issue of transfer from the simulation to the real world. And then there is the issue of transfer from the real world to the simulator, which is we currently have not addressed. How can we automatically, using real data, generate simulations? I think that's extremely important. Rich in data, rich in images, but rich in all sorts of other signals. What happens in the world, sound, speech. None of the simulators we have now has real language. Sorry.
So in computer vision now, there's also this noble quest of lifelong learning. So maybe can you comment on off policy learning when you were thinking about very, very, very long-term learning for robots, like you say, replay over many, many lifetimes of experience, being distributed, like cloud robotics and stuff like that. So how can you scale this out to many experiences over long periods of time?
So this by itself is only doing this sort of low-level closing the loop between motor perception and it's not addressing that sort of higher level. Of course, having memories is essential for like sort of creating. This is a very simple form of memory that I've shown you today, but eventually you do need to sort of start building a memory of all these past experiences. That memory will have semantic elements, and you need to learn how to travel in that memory, how to do what researchers call mental time travel. And that sort of mental time travel can also allows you to travel toward the future and plan, and to reach to sort of realize that you have mortality and create gods and all of those things. So it's very there's higher level things that are missing, and be able to connect. We need to create these memory systems that allows us to do mental time travel, as well as we need the mechanisms that enable us to write to those memory systems and retrieve with them from the memory systems without deleting. And I don't have time. I would have to go into the whole thing about replaying the brain and how the hippocampus and the cortex talk to each other. But for instance, your brain at night is working 100 times faster than it is during the day. And that's because you're doing a lot of replay and consolidating memories.
All right, let's thank Professor Taylor. Next up, we have Dr. Jeanette Bull, and she has done a lot of interesting work in interactive perception, and her talk title today is Interactive Perception for Perceptive Manipulation.
Sure. So thank you for the introduction and welcome everyone to my talk. So I have to say that this is the first time ever at a computer vision conference, although I'm in 10 years, and right now I'm working since 10 years on computer vision for robots. So I'm very happy and thank you for the invitation, and I think it would make sense that I have never published a paper at GDPR or ECCV or name them. In this talk, I'm going to try to build a bridge between computer vision and robotics, which I think has already been started by Jitendra Malik's talk. So, as I said, I've been working on this for 10 years now, and I've done lots of things, and they are very cool. So you can look them up on our webpage. I'm not going to talk about them today that much, okay? And also, I'm also using CNN, so if you're wondering whether it's connected. Anyway, so let's talk about why there's this funny divide between robotics and computer vision. I think, first of all, I want to mention that there is some work that on autonomous driving, basically, and understanding the visual input for autonomous cars where I think people have been publishing in both communities, like Andreas Geiger, for example. What you see here is some example pictures from the key data set. But really, this is one application area of robotics. What I'm actually mainly working on are robots that are able to interact with the world and manipulate the world. So doing tasks like this one, for example, that had to be performed at the DARPA Autonomous Robotic Manipulation Challenge. These are results from the team at UC at the University of Southern California. And really, the difference between these two application areas is that in the other one, the main thing you want to avoid is contact, right? You do not want to run into other cars or people or houses or whatever. And here, the main point is about exactly this, about making contact and not just randomly, but actually for achieving a particular task. And it turns out that this is actually the hard part, right? So this shows Garry Kasparov, 97, being beaten by Deep Blue at this point. And this was 97, but you see that there is a person there moving the chess pieces, right, for Deep Blue. So what we have somehow solved with gameplay or this, figuring out the right moves and so on, the process of actually doing this proposal interaction is what has not been solved. And this is actually, this thing has a name, it's called Moravec's paradox, which was Moravec mentioned in this particular book. And he said that, oh, it's so weird that we thought Rupert Hyde was playing these chess games or Go. But we have solved this, or somehow we can build machines that can solve this, but what is really hard is this interaction. And this is something that we're not consciously aware of, so therefore it's hard for us to understand or to reproduce these results, right? And well, I mean, this game, right? It's the same. So the person who moves the pieces is it's a person, it's not alphabet. Okay, so really, why has it been so hard? I think it's because if you have a robot in the world, it has only partial information about the world. And the world is also dynamically changing without the robot necessarily knowing exactly how it's going to change. Right? And so you've seen all this funny video of the robots trying to solve these tasks, right? And this is just a particular example from one robot failing in a very funny way. So it's supposed to turn this off. And it's not realizing that it hasn't grasped this law, and it's just unbalancing itself and keeping over that. And really, this is in 2015. I mean, these are smart people, these are not stupid people who work on these robots, they are smart. But yet, it's super hard to make this happen, and we have seen some interesting work on grasping and so on that looks more impressive. But still, there is this fundamental problem, and maybe for those of you who don't know, this challenge was teleoperated. So the entire problem of perception was actually outsourced to people, and while these people have, these are mainly like people who work on control, know everything about mechanics, electronics, and controlling and planning and so on, they don't know so much about perception, so they work a lot on the operator interfaces. Okay, so this is kind of weird, no? I mean, that we're still looking at kind of this things, and Jatinder had an explanation that he said it's because we have so amazing hands, while robots have so clunky hardware in a way. But I want to say that I don't think that this is the entire explanation using this particular video, which maybe some of you know. So this is obviously a trained surgeon using the Da Vinci teleoperation surgical system to do origami. And really, you see, these are just these two super simple grippers. There's no haptic feedback, and the person only has visual feedback. And yet, this person can do this amazing task, right? So you will just see how small it actually is in a second. So I think there's really something more than just, oh, we have to improve the hardware in isolation. There's something else that we haven't yet captured. And so actually, there are some, from all these DARPA challenges we Lots of people have worked on this and they learned something about it. And there are a few interesting papers on what they learned from these challenges. And this is from the team from WPI and CMU with Chris Atkinson, for example, on it. And what they say is that one of the main problems was making perception work on a real robot. So they took basically software that was open source available, and you can look it up which one it was. And they tried to use it on the robot, and it really just led to mediocre performance. Their insight was that they need to improve perception on a whole humanoid robotic system, and they need to actually find people who are interested in it. So if you're interested in it, they are looking for people. You know, I think I disagree a little bit with this, or I would like to go a step further. I would say that we don't even get to know what the relevant input is to these particular systems that we would need to use. So just to show you, so I asked my friends from IIT in Genoa, from the Dynamic Behavioral Systems Lab, to give me some footage from a robot who's actually walking instead of just flying or on wheels, right? So this is IQ, robotic dogs, and it's walking on a treadmill. You see it has a vision system, like actually a zero system on top of it. And what it wants to do is not actually walking on a treadmill, but you know, these people want to see this robot actually walking over really rough terrain, maybe going into disaster relief site, like that. And but I just want to show you the visual input from this. So this is basically the shaky camera input that they have to use to basically understand or somehow reconstruct the world. And it's very different from the kind of input that comes from a driving car, for example. And I think this is one of the problems that we consider perception as a separate problem, or the majority of people consider perception as a separate problem that has to be improved in isolation of whatever system it is put on. And this is just simply not true, as you can see here. There's just the action that this robot does influences the visual input. And in fact, you can learn this, right? How the action actually leads to particular visual input. Okay, so I guess one of my points is that that when we build robots, we still use this very traditional way of putting things together that follows the sense, plan, act paradigm, right? You sense once, then you assume you know everything about the world and it's perfect. Then you plan, and then you execute this plan mostly openly, right? And then I argue this is what happens. So actually, we have seen already this example this morning for setting the stage. So for those of you, I think there were some people who haven't seen this example, so I'm just going to briefly explain it again. So this is an experiment that shows that we should not consider perception and action separately and in sequence. We should actually somehow consider them together, and this is an experiment that was done in 1963. Somewhat cruel, I would say. So there are these kittens that were raised in complete darkness, and they were only seeing the light when they were put in this funny contraption. And there were two sets of kittens, the active and the passive ones, and the active would actually walk around, and you see their movement would actually move the passive kittens. And when these kittens were taken out of this carousel and asked to do particular tasks, like physiomotor tasks, the passive kittens, although they have been exposed to the same visual input as the active ones, they would terribly fail. Okay, so somehow self-produced movement with concurrent visual feedback is actually necessary to develop visually guided behavior. Okay, and there are more examples. For example, from Gibson, who also looked at the multimodality of our senses. So he looked at when we not only use vision, but also tactile information, how does our performance improve? So in this experiment, subject had to identify the two items that are exactly the same. And they would be really bad if they look at these pictures. They would become much better if they were allowed to rotate without touching, just visually rotating it. And they would be almost perfect if they could also touch them and feel it. So this emphasizes somehow the multimodality of our perceptual system. We 3D that doesn't just actually consist of vision. So I would argue that we actually have to close these loops. And interestingly, this arrow is very seldomly considered, or it's just being started to be considered, that action actually influences the sensing and makes it even easier to perceive. So there is an entire field, oops, that's not what I wanted to show, in robotics that I wanted to mention that is called interactive perception. So it's kind of an extension to active perception and it relates to the things that Jitendra has also shown, like about the pushing objects around and learning the response of this. And we've written a survey on this that's currently under review, but if you're interested in this field, I think that would be the starting point. Anyway, so these people from IT, what they did was, how did they cope with this problem that there's no good method out there that they could just take, and use as a black box and then good things happen. They developed a method that would actually be able to actively stabilize the camera, so the camera on top of the robotic dog would be moving to compensate for the motion, and they would be able to achieve better reconstruction. So, sorry, I jumped a bit. So this part is done without the active stabilization, and this one is done with. And they basically had to use the information from the action of the robot to move the camera accordingly, right? Okay, so the point from this part of the talk was really about that we need to, actually by knowing the action that the robot is doing, you can ease perception. And especially that the interaction helps you instead of necessarily being the problem. The same can be said actually about manipulation itself. So this is a video that has weirdly gained some popularity in the robotic manipulation community that shows like an excerpt from a show, The French Chef, also very old, showing Julia Child chopping potatoes. And what is shown here is that that she's using, while doing this, the environmental constraints. And there's not even a normal, like traditional graphic, except for the one where she uses to hold the knife. But everything else is about moving basically things around and exploiting the environment in a purposeful way to, to make this manipulation robust, but also safe for her, right? She doesn't want to drop into her fingers, so she's using her knuckles, for example. And this is really different from how grasping has been approached traditionally in the robotics community, where we have developed all these simulators that rely on perfect knowledge of the object and of the hand, and then there would be some metrics computed once the grasp is being established that relies on these contact points over there that are just point contacts to decide whether this grasp is a good one or not. But also in robotics, we just recently learned that it doesn't make these metrics that were developed in simulation, they don't really make sense. They don't transfer to the real world. They are essentially relying on assumptions that are not true in the real world. So what works much better and what makes much more sense is to do what Julia Child is doing in her video. She's namely to use the environment to make content instead of avoiding it. And this actually led to the success of this team and all of the other, there were 3 winning teams and UC was one of them. And all 3 of them had this insight that they have to use this contact with the environment to make manipulation robust. And so here's the interesting part for the vision community. The kind of visual perception that was used for this system was super simple. I mean, it was even a bit crappy. It didn't work very well. But what made this a winning team in a challenge, dark, I mean, it's serious, was this contact exploitation to deal with these visual, with this noise and with the uncertainty that came from the vision system. Okay, that's the important part. So yeah, so another maybe example in this direction is the current developments also in robotics that are kind of important, that there are more and more soft robots, so robots that are safe when they're around humans, but also when they are interacting with the environment. And this is a particular video that shows the first version of the software developed by TU Berlin. And they can really grasp anything if it's somewhat correctly placed in the right position, right? And the interesting part is also, there's no vision involved. There's also no sense of feedback actually in the hand. This just gains robustness and grasping by being compliant. In this case, it's passive compliance. In the previous case, it was active compliance. Of course, I mean, still this is limited, right? If you add vision to the loop, there's more generalization that's possible. But still, what I want to mention here is that you know, it doesn't make sense to necessarily assume certain visual input to this, right? It's not important to exactly and accurately know the process of the object or the shape of it. It doesn't know about this object. Okay, so just maybe one of the main take-home messages from this talk is really that interaction seems to be the problem, but it's actually not. It's the solution. And it's the solution in terms of manipulation. So, you know, if you get into contact and interact with the environment as much as possible, you actually make manipulations robust. And it also is the solution for perception, because when you include knowledge about the action that you perform, you actually are getting better at perceiving, because you generate a richer sensory signal that wouldn't be there without interacting with the world. And what that also, so to leverage these two concepts, you need to think about them in an entire robotic system that closes these perception action loop. Otherwise, it won't be possible to do that. And I think the big question is, what are these systems, or how are they structured? And I want to just briefly get a bit into the kind of architectures or control loops that are considered normally in a robotic system. So this, for example, is a standard control diagram of a feedback loop in motion generation, right? So you have some reference signal that you want to track. Someone has generated it. It's checking whether the robot has already reached that reference. And given this error between what you want or what the robot wants and where it is currently, it computes a control input that is sent to the robot. And then in the next time step, which is usually just a millisecond ahead, it checks basically the current state of the robot, and the feedback is used to compute the next error. So usually what is done, in robotics is that these sensors are only joint sensors or torque sensors, right? Seldomly there's actually vision included in this loop, or you know, it's this is somehow the missing piece, that vision or tactile sensors are in this loop as well. And usually the state or the particular reference trajectory is very, it's a very simple coding of maybe joint engine and things like that. But the question really is, like, if you include also visual sensing and tactile sensing, how do you provide the reference, in what form do you provide the reference that you want to achieve, and how do you compute the error between the current state and the last one? Okay, so I think I have 5 more minutes. Is that true?
3 to 4 more minutes.
So I'm going to talk a little bit about the things that we're doing. So what we are working on in our lab is really systems that do exactly this, that close these loops. And this is just this, like a already simple diagram of how this could look like. And I'm not going to explain all of the details here. I just want to, the important thing to take it away from this image is that there's loops closed everywhere. There's vision feeding into motion optimizers that then send their messages to the robot and then are again checked by the vision system. There's learning going on with the dynamics model. And all of these are running at the same time and in real time as well. So we actually looked at a particular problem of tracking objects that ought to be manipulated for a robot. So it has to happen in real time, and it has to be robust, and especially also in manipulation, robust to inclusions. So we developed a system that does that for us, and we are also correcting for errors in the robot models that we have by also visually tracking them. And all of these we could actually put exactly in feedback loop like this. So our error here, or our reference trajectory, is a particular pulse of the robot hand relative to the object, and we want to basically minimize that error by sending the right control input to the robot. But in a way, this is still hard-coded, right? So we rely on knowing actually the object model, and basically we assume that's the underlying assumption. So an interesting question here would really be like, how can you provide this feedback also for objects that you don't necessarily know? Okay, so this was like one simple control loop that is usually considered in robotics. There are of course many more, and a particular popular one is the mixture of this feedback controller that I showed you before, and an inverse dynamics model that tells you something about and but this work partially from our lab up here. Sorry. Where we used a similar robot to what I showed you before to do a particular task. And this robot or the system that's used here relies really on all the sensors that the robot has, so tactile, force-stroke sensing, and vision, and uses that to be actually robust to a lot of perturbations. By the way, this system relies also a lot on learning by demonstration, so a person has actually demonstrated what the good skills are. What the robot does here by itself is to decide how to switch between these skills that you learn from a person when perturbations happen. And I think many of you have probably seen the work by Sergey et al., where they also learn a particular state representation of the visual input and also rely on learning by demonstration, and thereby do these kinds of tasks. Okay, so maybe the way the work that Jutta has talked about today about poking objects and learning the dynamics model of its own action, this I think comes in here, namely at the point where the reference trajectory is generated. So if you know the dynamics model of the world as a response to your action, then you can optimize over it and provide a reference trajectory that is fed into these kind of systems. All right, so I want to conclude my talk with basically repeating the take-home messages, but also posing some questions. So first of all, I want to mention again, like interaction seems hard, but actually it's the solution to manipulation or to robust manipulation and robust perception as well. And there are still many interesting questions that we don't yet have an answer to. Namely, what is, for example, what are good representations of this multimodal feedback that we have on a robot to adapt these interactions? How should the system be structured that these models are actually embedded in? And particularly important in robotics is what the good trade-off is between data and prior models. On a robot, I mean, unless you're Google and you have a farm, you won't be able to generate millions of training data points. And also people don't seem to need that to actually perform personally in the world. And yeah, of particular interest is also how to learn these models that reflect this causal relationship between the action and the perception or the sensory response that we get. Okay, so thank you very much for your attention. And I think that's the particular picture on the trade-off between data models. Thank you very much.
Thank you, Dr. Bo. I can take a couple of questions. If we can.
Hi. Have you ever tried incorporating action recognition into these models?
So I personally have not, but I know of work that will also be published by, I think, the computer vision community, where recognizing what people, the action of people simultaneously with the object that's being manipulated helps to understand both better the action and the object. So yeah, that definitely makes sense to combine.
You talked about closing the perception action loop, but usually what the eye tracker systems see is that usually when people manipulate objects, they just look at it for a second, and even before making the contact, and then they already are making the contact. Yeah. So can you comment on how we can incorporate this in?
Yeah, so that's actually an interesting experiment that we've seen in your talk with the sandwich making, right? So you could actually see, if you ever find it online again, you can see that people are actually ahead of the action that they do. So when they have grasped something, they are already looking at something else. So my particular hypothesis there is that people pay attention until contact is made, because that's a very difficult thing to model and maybe to predict the effect of it. And once this is established, they have whatever they needed to have in their hand. Maybe tactile perception takes over and they can allocate visual attention somewhere else, right? So it somehow shows that perception in people seems to be multimodal, and they know what sensory channel is basically reliable and important. And same should be learned in robots, right? Like along a particular time extended behavior, what are at each moment in time the important sensory channels that the robot should rely on to adapt? I think that is what you could learn there. And I've done some work on, so basically this work that I've showed with screwing the cap on the bottle, that one actually learns for time extended behaviors what the important channels are, and pays attention to those to decide maybe to do a reactive behavior or some corrective movement, things like that. Thank you. Anything else?
Thank you. Thank you, Dr. Bose. I think we're running about 15 minutes behind time now, but we can take a quick, maybe a 10-minute coffee break, slightly curtailed, but we'll